Okay, so let's get started. So let me start with a summary first. So far we've looked at a different way of doing classical mechanics. And the last method that we looked at is the so-called D'Alembert's principle. And so D'Alembert's principle, it came from taking the idea that if you wrote Newton's law as F plus minus ma equals to 0, so you take into account this minus ma and pretend like it's a force, the inertial force, then you can treat this like a problem of statics instead of dynamics. And so we did a lot of math last time to get this in a nicer form. Where for each degree of freedom, Qj, you have the equation d by dt of di capital T by di Qj dot minus di capital T by di Qj equals capital Qj, where T is the kinetic energy of the system. And so for a set of n, capital N particles, T is the total kinetic energy, sure. It's the sum from I equals 1 to capital N of the kinetic energies of all of the particles. And then Qj, that is the generalized force in the j direction, and that's given by some applied external force dotted with di Ri by di Qj, where Ri is the vector of where that force is applied. So we haven't actually done any examples where we've applied this. But is there any questions about the derivations or the philosophy of the method? Okay. So on Thursday, the assignment will be on. There will be a new assignment. It will be on virtual work in D'Alembert's principle, and we'll also do a couple of more examples of applying D'Alembert's principle. So let me do one example now, a more general example that'll be relevant to the next part that we're going to cover. How much space do we have? Let's just start on a new page. So this is example 3.6 from the notes. I was hoping that we would get to it on last Thursday, but we had some technical issues. So I'll just do it today. So let's use D'Alembert's principle to obtain the equations of motion of a particle in a gravitational field. Well, I'd say in a conservative field. Such as gravity. So a conservative field, remember, so you remember what a conservative field is. A conservative field is a field where the force from that field does no network on a closed path. That's what that integral is, right? The circular integral. So for example, gravity does no network on a path if the starting and end points are the same. That is one way to say force is conservative. So if you have a force from a conservative field, you can write the force to be minus the gradient of what we typically call a potential. All right, so for example, if phi were gravity in one direction, the force were gravity, then phi would be mgh, and the force of gravity would be minus d by dh of mgh, so it would be minus mg. Okay? So we know the force is given by the gradient of some potential function. Okay? And then we want to use D'Alembert's principle to get the equations of motion. So we want to know how do we describe the degrees of freedom of the system as a function of time. The equations of motion are the equations that give us that description. So first we need to identify how many degrees of freedom are there. And that's the same for just about any problem in this course. The first part is typically identify the number of degrees of freedom. So this is a free particle in three-dimensional space. So there are 3 degrees of freedom. And so let's just choose the Cartesian coordinates as our 3 degrees of freedom to describe our system. In this case, our system is a particle in a gravitational field. Okay. So the next step, if we look at D'Alembert's equation, right, what we need is this capital T, and presumably since we're taking the derivatives of the capital T with respect to the Qj, we want to express the total kinetic energy in terms of the degrees of freedom. So let me just say, recall in the summary here that we can always write the kinetic energy T in general to have mathematically a form that's something like the sum over J equals 1 to n, the number of degrees of freedom. So it'll be a double sum over J and K, and you can write in general the kinetic energy as some term times the product of the velocity. And then there could be potentially a term that's just linear in the velocity, and then there could be a constant term. Oops. very general, we can always write the kinetic energy in terms of the generalized coordinates. Right? So here we want to do the same thing. We want to write the kinetic energy T in terms of our generalized coordinates, which are the x, y, and z Cartesian positions. So that's very easy. That is the easiest kinetic energy to write down. And we can write T equals a half m. So there's only a single particle, so there's no sum over n particles. And the kinetic energy would be x dot squared plus y dot squared plus z dot squared. Right? X, y, and z are the positions of the particle. X dot, y dot, and z dot are the coordinates or the components of the velocity in x, y, and z. And then v squared, the velocity squared, which you need for the kinetic energy, would be x dot squared plus y dot squared plus z dot squared. Okay, so we've written the kinetic energy in terms of our degrees of freedom. Now the other term that we need, the other thing that we need for D'Alembert's principle is Qj, the generalized force. So let's write out the generalized force. So it's the sum over all the forces for all the particles. And that's just a definition here of di Ri by di Qj. So we all have only one particle, right? And F could be the net force on that particle, but there's only one force in this case. Our vector R, so Ri, which is, there's only one of them, right? That is simply the force of gravity. It's where the force is applied. And this is a point particle, so the force is applied at the position of the point particle. So the position of the point particle is given by x times x hat plus y times y hat plus z times z hat. Right, where x, y, and z are the positions of the particle. And then we also have that the force F, remember we wrote the force F as the gradient of some potential, so the force F, if I write it as a vector, it would be minus di phi by di x hat minus di phi by di y hat minus di phi by di z hat. And there's a minus sign in front of the gradient at the top. And that's just the definition of gradient, right? So if I take the dot product now, first let me think of exactly what is Qj. So how many Qj's are there? There's only one F, right? There's only one particle. I goes from 1 to capital N, which is 1. But the Qj, remember the J is the label of the degree of freedom. So there are 3 different Qj's, right? Because there's 3 degrees of freedom, X, Y, and Z. So there are 3 different Qj's. So the first one I'm going to call Qx. It's the Qj that goes with our first degree of freedom, which we've called X. So Qx would be the sum from I equals 1 to capital N of Fi vector dotted with di Ri, and now di Qj is di X. Right? So the sum is only over 1, so if I look at my di Ri by di X, if I look at Ri up here, di Ri by di X, only the first term has an X in it. And when I take the derivative with respect to X, it's di by di X of X times X hat. And so that's just X hat. So this is the dot product of Fi which would be minus di phi by di x hat minus di phi by di y hat minus di phi by di z hat, and that's got to be dotted with, oops, that's got to be dotted with d by dx of x hat plus y hat plus z hat, right? And d by dx of that is just x hat. So I'm dotting the terms with the phi's to the term with just x hat. So that's going to pick out only the x hat component, and so that's going to give me minus di phi by di x. And so similarly, I mean, this is hopefully, once you get used to it, you can do this in your head. So by the same token, you're going to get qy equals minus di phi by di y, and you're going to get qz equals minus di phi by di z. So we want to put this all into D'Alembert's equation now. So remember, D'Alembert's principle was d by dt of di by capital T di qj dot minus di t capital T by di qj equals capital Qj. And this is true for all j. And so j goes from 1 to 3, right? So we have Q1, Q2, Q3. That's equal to x, y, and z, our 3 degrees of freedom. So the first thing we need to do is we need d by dt of di capital T. So now I'm going to do when j equals 1. So that will be di by di x dot minus di t by di x equals qx. Alright, so this is the first equation. Remember, so D'Alembert's principle is true for all j. There's 3 possible j's for 3 degrees of freedom, and so then we write this out 3 times. So the first time we use qj equals to x, right? So di by di qj dot is the same as di by di x dot. So remember, t is a half m x dot squared plus y dot squared plus z dot squared. So we need di capital T by di x dot. So if I do d by dx dot, I have d by dx dot of a half m x dot squared. So that's simply mx dot, right? The squared cancels the half. And then we need di t by di x. Now if I look at t, it doesn't depend explicitly on x, right? So that's equal to 0. And then finally, I really need d by dt of di capital T by di x dot. So that's d by dt of mx dot. M is a constant, so then it's d by dt of x dot, and we call that double dot. So it's mx double dot. Alright, so mx dot is m times the speed in the x direction, and mx double dot is m times the acceleration in the x direction. So that's really the same as the x component of acceleration. and we'll find this out much later, but d by dt of di x dot is also the x component of momentum. So you can forget about that now, but it will turn out to be practical later. Alright, so now we actually have everything. We have both the left side and the right hand side of the equation, so we can put this all into D'Alembert's principle. And so then we get the x component of D'Alembert's equation, right? So the left hand side is going to be just mx double dot, and then the right hand side is going to be minus di phi by di x. But this minus di phi by di x is the x component of whatever force there is. And so I would say that's expected, right? Because that's what you would expect from Newton's second law. In fact, it is Newton's second law. It's saying that mx double dot equals fx. So that's Newton's second law. Well, remember what we started out with is this abstract-looking D'Alembert's principle with the kinetic energy and this weird generalized force. So it turns out when you take the time derivative of di t by di qj dot, and t doesn't depend on qj, then you just get mx double dot. So in the math, I mean, it's trivially the same thing, and you'll get the same equations for y and z. Sorry, that's going to be a little y in the second equation. Okay. So any questions about that? On Thursday in the assignment in the tutorial, you'll get to apply this a couple more times. So the general theme here is that you need to identify the number of degrees of freedom, and then you need to write out the kinetic energy in terms of those degrees of freedom, and then you need to write out the generalized force in terms of those degrees of freedom. And then you can plug everything into the equation and hopefully get the correct equations of motion. So let me note now is a mathematical curiosity in this example. So consider, let's introduce a new thing called L. Let's call it to be t minus phi. So I know that phi turns out to be potential energy. Right, the thing that gives rise to a force when you take the gradient turns out to have the right units of energy. And so I know mathematically I can see what's going to happen. So I can build this new thing which I'm going to call L, and I'm going to say it's t minus phi. And then suppose you want the stationary value of the integral that's given by S, let's say, of L dt. So in this case, this would be the integral from a to b of, like I said, t minus phi. So t is a half m x dot squared plus y dot squared plus z dot squared, right? That's t minus phi. So this function L here is a function of x, y, and z, because phi could depend on x, y, and z, right? And then also depends on x dot, y dot, z dot. In this case, it doesn't depend on z. So we know how to do this, right? We know how to find the stationary value. So in this case, this is a problem of the calculus of the variations. So we need the calculus of variations to find the functions x of t, y of t, and z of t that give a stationary value to the function capital S, which was the integral of L dt, the definite integral. Okay? So if you remember from the calculus of variations, if I have to show this for the assignment, that for each of the functions, so in this case there's three functions, L depends on three functions, right? So you get an Euler-Lagrange equation for each of the three functions. So you have to use the Euler-Lagrange equation. And S will be stationary if d by dt of di L by di qj dot minus di L by di qj, equals 0 for all qj. In this case, qj is x, y, or z. So remember, L is a half m times x dot squared plus y dot squared plus z dot squared minus phi. So di L and phi depends on x, y, and z. Right, it's potential energy, so it depends on position. Just like gravitation, the potential depends on position, not speed or anything like that. So what we need to put it into the Euler-Lagrange equation, we need di L by di, so qj dot, when qj is equal to x, that'll be di L by di x dot. So di L by di x dot, it's the only term that depends on x dot is a half m x dot squared, so di L by di x dot is just m x dot. And the term that I really need is d by dt of that, so it's d by dt of di L by di x dot, and that's mx double dot. And then the last term that we need in the Euler-Lagrange equation is di L by di x. So if I look at the kinetic energy term, there's no x's in there, but the phi term does depend on x, right? So di L by di x is minus d phi by dx, right? Because the L part that depends on x is minus phi of x, y, and z, and so di L by di x is minus di phi by di x. So if I put this into the Euler-Lagrange equation for x, I have all the terms now. So I have the d by dt term, so that's mx double dot, and then it's minus the di-L by di-Qj term, so that's plus d phi by di-x, di-phi by di-x, right? Because that term is minus di-phi di-x, so I have to minus it there. So that's equal to 0. And then of course if I move it to the other side, mx double dot equals minus di-phi by di-x, just as we had before. Of course you'll get the same for y and z. So we've only done a mathematical curiosity, but it seems that if we build this function capital L as t minus the potential, in this very specific case, then the equations of motion is given by requiring that the integral of L dt is stationary. That turns out to be equivalent to D'Alembert's principle, and we saw that gives Newton's second law as well. And so the subject of the next chapter is going to be a very detailed understanding of what this capital L is. And so in fact, we've done our first problem here where we've used the Lagrangian. L will be called the Lagrangian. Okay, so yeah, I'll leave that there for the example. Any questions? Okay, so there's an additional section in the chapter of the written notes on inertial forces, and you should read that, but I'm going to skip it. The gist of it is it expands on this concept of D'Alembert's principle, where if you consider the force of inertia as a force, so the ma, you pretend that that's a force, then you can say that the sum of the forces is 0. And that's somewhat similar to saying that you can find a frame of reference that's instantaneously at rest. So consider, for example, an elevator, a vertical going elevator. It turns out that you can't tell the difference between that elevator sitting still at the surface of the Earth, so you experiencing a force of gravity downwards. You can't tell the difference between that or the elevator being in free space, so no gravity at all, and accelerating upwards with acceleration due to gravity. You can't tell the difference between those two. And that's similar to saying that I can make this force of inertia just like another force. So that's like finding a frame of reference where the body is at rest because of this additional force of inertia. Okay? And so the final section of the chapter just does that mathematically. But I don't think it's super interesting. So I want to get started on chapter 4. And then on Thursday, we'll focus on problems that are related to chapter 3. So chapter 4 is one of the meatier chapters. It'll take us a while to get through. And it really has now a lot of the material for this new method of doing classical mechanics. So everything until now was really set up for chapter 4. So in this chapter, we will introduce what's called the Lagrangian, L. So L is a function of the generalized coordinates, the generalized velocities and time. It's a scalar, and it completely describes the system. So that's in line with our original goal. Our original goal is to find a description of a mechanical system that doesn't require us to use vectors, and it's purely scalar and purely based on things like energy. So D'Alembert's principle was almost there, right? The left-hand side of the equation with the kinetic energy, that did not require you to draw any forces or vectors. You can just calculate the kinetic energy from transformation coordinates, or if it's in Cartesian coordinates, you can write it down right away. However, the right-hand side of the equation with the generalized force, that you will probably be hard-pressed to do in your head, especially if you have to draw a vector where the force is acting and try to figure out how to do the dot product with the di-r by di-qj term. So it's in the right direction, but it's not completely there. And so the Lagrangian method is really the last step in getting everything to work out as scalars. Of course, there's some times where you just can't get rid of vectors, like non-conservative forces or weird forces of constraint. But generally, you can pretty much completely get rid of the vector description. Okay. So I want to now revisit the example that we just did and do it a little bit more formally. So what we're going to do in this chapter, we're going to derive these equations of motion, these Euler-Lagrange equations, in different ways, because there's different ways that you can get this Lagrangian and conclude that it correctly describes the system. And so the first way we're going to do it now is to do it from D'Alembert's principle. So we're just basically going to redo exactly the same example. And then later on we'll look at Hamilton's principle, which is this notion of trying to find a stationary value in an integral. So let's start over again with the case of the single particle in a conservative field. So let's do the Lagrangian from D'Alembert's principle. So let's consider a single particle in a conservative field. So in the case of a single particle in a conservative field, so first let's say that let V equal a conservative field. And that field gives rise to a force capital F given by grad V, minus grad V, sorry. And so that's equal to, in vector form, it would be minus di v by di x hat plus di v by di y hat plus di v by di z hat. So I want to start by remotivating that V is really the potential energy. Okay, and you should have done this in first year physics when you demonstrate that when you derive a function for the potential energy. So we want to show that V is really potential energy. Potential energy, remember, is a function that depends only on position, not the path taken between the two positions. And so you can calculate the change of potential energy by evaluating that function at the beginning and at the end of some path. And you don't need to know what path was taken, right? That's the goal of using things like potential energy. And so to derive the formula for potential energy, we need to know the work done by some force in going from some position R1 to some later position R2. And then the work is the dot product of the force with the displacement. So with our value of the force, this integral becomes the integral from R1 to R2. Now I can plug in my force vector, so that would be di v by di x hat plus di v by di y hat plus di v by di z hat, and then that's dotted with dr. And so if I write dr in Cartesian coordinates, that would be dx x hat plus dy y hat plus dz z hat. And so if I take the dot product, I have di v by di x dx plus di v by di y dy plus di v by dz by di z dz. Right? So that's integral from R1 to R2 vector minus, sign in front of the integral, I'll put it, and I have di v by di x dx plus di v by di y dy plus di v by di z dz. So that's equal to minus the integral from R1 to R2 of dv. So the integral of dv is easy. That is just v. And so then when I evaluate the integral, I have v at R1 minus v at R2. And so if I want to write that with the redundant minus sign, the total work done by the force is minus v at R2 minus v at R1. So the work is minus the change in v hence, V really is what we like to call potential energy. So let L be defined as T minus V. along with the Euler-Lagrange equation, you must always remember L equals T minus V. In fact, you can forget the Euler-Lagrange equation, but you should never forget that L equals T minus V. So L we call the Lagrangian. And it's equal to the kinetic minus potential energy. So in this case, we only did a single particle in a conservative field, but it will be true in general that it's the total kinetic energy minus the total potential energy. Sometimes people call this the excess kinetic energy. Right, if the kinetic energy is bigger than the potential energy, maybe you could escape the gravity of Earth or something like that. So that's why sometimes T minus V is called the excess kinetic energy. But that's more of like an old school term than anything useful. Okay. So let's go back to D'Alembert's principle. So let me just write it out. D'Alembert's principle is d by dt of di t by di qj dot minus di t by di qj equals capital Qj. So capital Qj is the generalized force. That was the sum from I equals 1 to capital N. Force Fi dotted with di Ri by di Qj. Now let's extend this to maybe there's more than one force on the particle. Alright? So let's work on this capital Qj term. So capital Qj, I'm just going to start by rewriting the definition. Capital Qj is the sum from I equals 1 to capital N of Fi dotted with di Ri vector by di Qj. And now let me split this up into conservative and non-conservative forces. So let's say it's the sum from I equals 1 to N of the number of conservative forces, NC. So that'll be Fi, and I'll put a C on the force, dotted with di Ri by di Qj, plus the sum from I equals 1 to N sub NC for non-conservative forces, Fi subscript NC dotted with di Ri vector by di Qj. Okay, so that's a non-conservative force. And Fc would be a conservative force. Okay, so this is one particle with several forces applied on the particle. And those forces, some of them may be conservative and some of them may be non-conservative. And then we'll see later that mathematically that's indistinguishable from just having multiple particles with multiple conservative and non-conservative forces. But for now, you can just think of this as one particle, multiple forces. So the last term there, the non-conservative force, maybe you guessed it, but there's not really much you can do. The whole point of doing this is that we want to put in the potential energy into the conservative force term. So the last term, I'm just going to drag around everywhere, but I don't need it. I'm going to shift to the left here so I have a bit more space. So this is now the sum from I equals 1 to capital M for the conservative forces. And now my SI for a conservative force, I'm going to write it in. So it's minus the gradient of the potential energy. So there might be more than one conservative force VI, so it's going to be there's more than one potential function V that gives the different potential for conservative forces. So Fi means it comes from a potential VI. So if I write out FIC, so it'll be di VI by di X, X hat. So I put the minus sign up front, then I have a di VI by di Y, Y hat, plus di VI by di Z, Z hat, and that's dotted with the di Ri by di Qj, so that's dotted with di by di Qj of the Ri vector, and so that'll be the xi position of the force, I, plus y hat, plus zi, z hat, and then plus the non-conservative term. So that's going to be equal to, let me put the minus sign out front, then it's the sum from I equals 1 to n sub c of di VI by di X, di XI by di Qj, plus di VI by di Y, di Qj of Yi, plus di VI by di Z, di VI by di Qj, plus the non-conservative side. Now the indices sub I that are on the x's, y's, and z's there are redundant because we're talking about particles, and so all the forces are on the one particle. So if you look at this term, di V by di X by di Qj, plus di V by di Y by di Qj, plus di V by di Z by di Qj, that's the same thing. That's really the chain rule, right? And so that's the same thing as saying minus the sum from I equals 1 to MC of di VI by di Qj, plus the non-conservative term. So let me start on the page. So if we let V equal the sum from I equals 1 to MC of the VI, then the first term, which is a sum from I equals 1 to the MC of di VI by di Qj, that's equal to simply di V by di Qj. Right, if I bring the sum inside of the di by di Vi, then I have the sum of the VI's, which is just the total V. Hence, we get that Qj is equal to minus di V by di Qj. Remember, there was a minus sign on here, plus the non-conservative part, which was the sum from I equals 1 to n sub nc of fi sub superscript nc dotted with di Ri by di Qj. So putting that back into D'Alembert's principle, we have d by dt of di capital T by di Qj dot minus di capital T by di Qj. And that's got to be equal to the Qj. So the Qj is minus di V by di Qj plus the sum over the non-conservative forces. Okay, so let me rearrange this a little bit. I'm going to bring the di V by di Qj to the other side. So that's d by dt of di T by di Qj dot minus di by di Qj, and I'm going to write this as T minus V. And that's got to equal to the sum over the non-conservative parts. Alright, so if I bring the term with the di V by di Qj to the left, it becomes plus. Then I factor out an overall minus sign so that I can write it as T minus V. Now, if V does not depend on Qj dot, so when I say V doesn't depend on Qj dot, I mean that di V by di Qj dot equals 0. Right, so if the potential energy V doesn't depend on the generalized velocities, then, or that, I mean that's the same thing as saying di V by di Qj dot equals to 0. In that case, di by di Qj dot of T minus V is the same as di by di Qj dot of T, because di by di Qj dot of V is 0. So only when V doesn't depend on the generalized velocity, right? Or another way to say it is that di L by di Qj dot is equal to di T by di Qj dot, where L, remember, is this C minus V. So finally, we can rewrite D'Alembert's equation as d by dt of di by di Qj dot of T minus V minus di by di Qj of T minus V equals the sum over the non-conservative forces. And if we write this with L as T minus V, this gives us d by dt of di L by di Qj dot minus di L by di Qj equals the sum over the non-conservative forces. So together with the definition of L, I think these would be the two most important equations to remember. And the T minus V, L equals T minus V, is probably the most important equation in physics to remember, or definition at least. Okay, so this equation is almost like the Euler-Lagrange equation. It's exactly like the Euler-Lagrange equation when there's constraints involved. So that's what makes the not equal to 0. And if there are no conservative forces, then it's exactly the same as the Euler-Lagrange equation. So there aren't many forces in nature that are not conservative. So this term on the right is often 0. So a non-conservative force, friction, typical non-conservative force, right? So if you had a problem where you have friction, you would have to include friction on the right-hand side. Now, that's actually a limitation of your description of the system if you have to include friction. In principle, you could use a much more complete description of your system where the friction force now is really an internal force, or it's something to do with friction really comes from the electromagnetic force, and it's the force of attraction between the atoms and the two objects, right? And so if you include a proper electromagnetic description of this friction, then you can describe it in terms of conservative forces. And so it turns out that if you're accurate enough in how you describe the system, you're not going to end up with any non-conservative forces. Because fundamentally, all the forces of nature come from, the four forces: gravity, electromagnetism, and strong and weak nuclear forces. And those are all conservative forces. So in principle, a complete description of the system wouldn't involve the term on the right. But most of often our description may require the need to include a non-conservative force. And so that's what we'll do right now. We'll do an example of using this new method for solving a problem. Okay, so this really has now, if there's no conservative forces, we've actually come out with our goal, which is a way of describing a classical system without using vectors. Right? So if there's no conservative forces, then it's only the left-hand side of this equation that you care about. And so you only need to be able to calculate L in terms of the Qj. And L is the kinetic energy. You can write out the kinetic energy without drawing any vectors. And same with the potential energy. You don't need to write out any vectors to figure out the potential energy. So you can write out purely scalar quantities as long as you've written them out in terms of your degrees of freedom, Qj, and then you have the mathematical procedure that will give you the equations of motion. So it's conceptually a little bit different than what you're used to doing, like drawing the forces and getting F equals ma, but it turns out it's incredibly powerful, and this is the way that modern physics is done. Even, I think maybe you're starting to learn quantum mechanics, and then in grad school, when you're very advanced, you might learn quantum field theory, and quantum field theory is all based on the Lagrangian. So the standard model of particle physics, for example, when people say the standard model of particle physics, they are really talking about a Lagrangian. People have written down a form for the Lagrangian that seems to accurately describe the experiments that we can do in particle physics. So it's all based on Lagrangian, and it's all based on these terms of potential energy and kinetic energy. Okay? So it's really the foundation of physics is this function t minus v, this Lagrangian. It's very important. So let me do an example. How could you possibly solve a problem with this t minus v? And I'll do it super slow, even though it's a super trivial problem. Okay. So this is example 4.1. Because it's a little bit different way of doing physics than you're used to. Right? This is all about doing it with scalar quantities. So you always need to think about degrees of freedom, generalized coordinates, things like that. That's where the real creativity in solving the problem is setting it up. So let's consider the classic problem of a block sliding down a hill. So this is a block of mass m. We have an origin, which we've written down here. And we're told that our block, there's a constant friction force F that's applied here. Okay, so this is a block sliding down an incline subject to friction F. And I'm just going to leave F as the friction. I'm not going to make it a coefficient of kinetic friction times the normal force or anything like that. Something that you could do trivially. But let's just say it has a magnitude F. Or it's a vector F. So the first step in all these problems is always to identify the number of degrees of freedom. So how can I describe my system? That is where the block is. How many numbers do I need to describe that? So there's only one degree of freedom. Right? So you could start off where there's 3 possible degrees of freedom, x, y, and z. The block is constrained to be on the plane. So z is always equal to 0, so that's one constraint equation. So then you only have 2 possible degrees of freedom. And then there's a final constraint that the block must be on the incline. And so you can relate x and y, right? If you know x, you can find y, or vice versa, because y over x is tan theta. And so that's your second constraint equation, that y over x is tan theta. So you have 2 constraint equations, z equals 0, and y over x equals tan theta. And so you have only 1 degree of freedom. All right. What am I going to use as my degree of freedom? So let's say we have an angle theta here, which is a constant. Well, to me, a natural thing to use as degree of freedom is this distance, which I'm going to call r. And it's the distance from the block to the origin. So my 1 degree of freedom, I'm going to choose r as the distance to the origin. So that's the first step. Now remember, we want L, which is equal to t minus v. So we need t as a function of r and v as a function of r. And t in principle could be a function of r and R dot. Whereas V, so far what we've done is we've asked that the potential only depend on position, right? We made that crucial step. We made that crucial step up here where we said that the potential energy doesn't depend on the velocities. So only T can depend on the velocities. Saying that V doesn't depend on the velocities allowed us to put V inside of the derivative dot by dot Qj dot. Okay? So we need to know T in terms of R and R dot. So T is always easy to write out in Cartesian coordinates. T is always a half mx dot squared plus y dot squared plus z dot squared. So what we really need is x dot, y dot, and z dot in terms of R and R dot. So let's start with x. So the x position is given by r cos theta. All right, if you look at your diagram, the x position of the mass is r cos theta. So if I take the time derivative of that, x dot, so theta is a constant, right? So d by dt of r cos theta is simply going to be r dot cos theta, because theta is a constant. Same with y equals r sine theta. And so if I do y dot, I get r dot sine theta. And then z, we said that z is always equal to 0. So t is equal to a half m. So x dot squared is r dot squared cos squared theta. And y dot squared is r dot squared sine squared theta. So if I factor out the r dot squared, then it's a half m r dot squared times cos squared theta plus sine squared theta, which is 1. And so that's a half m r dot squared. So that's good. We've got t in terms of r and r dot. And in this case, it only depends on r dot. So now we need v. So v is the potential energy. So let's think of what conservative forces are acting on our body that lead to conservative forces, or potential energies. And so there's only gravity in this case, right? So we have gravity is acting on our body, and what's the potential energy from gravity? It's mgy, right? That is the potential energy due to gravity. It's very easy to make mistakes here. So you have to write out your potential energy in terms of your generalized coordinates. So for now I've written in terms of y, because y I know easily how to calculate gravitational potential energy. Does it have the right sign? Should there be a minus sign in front of that? You should always ask yourself. In this case, no, right? Because if y gets bigger, I have more gravitational potential energy, so v gets bigger. So that makes sense. Now I want v in terms of my generalized coordinate, which is r. So it's mg. So I know how to express y in terms of r. Y is r sine theta. Okay, so we're good. We've got t. And we've got v. And the only thing that's really missing for us is the right-hand side of the equation, where we have the generalized force due from the non-conservative forces, right? So finally, we need Qj from the non-conservative forces. So that's the sum from I equals 1 to capital N of our non-conservative forces times di Ri vector by di Qj. Alright, so there's only one Qj, right? So Qj equals R. So capital Qj equals, capital QR. N equals 1. There's only one force, and that force, Fi non-conservative, is our friction force. So I'm going to have to write out our friction force F as a vector, and I'm going to have to write out the vector Ri as a vector as well. So let me write out our force as a vector. F is equal to its magnitude, and then cos theta x hat plus sine theta y hat, right? The force is positive x and positive y. And then our vector r hat, where the force is applied, is the same thing. It's going to be r cos theta x hat plus sine theta y hat. And the part that we need is di Ri by di Qj, right? And so that's di by di R of the vector that we have up there, which was R times cos theta x hat plus sine theta y hat. Of course, I take di by di R of that. It's just trivial, and I get cos theta plus, or cos theta x hat, sorry, plus sine theta y hat. Hence, QR is F dotted with di Ri by di R. And so if I dot F with this, I have F times cos theta x hat plus sine theta y hat dotted with cos theta x hat sine theta y hat. So that'll be F. The x components in the dot product will give cos squared, and then the y component will give sine squared. And so the total generalized force is just F. So we have all the terms now, right? So we have T of R and R dot, V of R, and QR. So we put that into the Euler-Lagrange equation. Or no, let's not call it the Euler-Lagrange equation for now. Let's put this into our equation of motion. Remember, our equation of motion was that d by dt of di L by di R dot minus di L by di R equals Qj for the non-conservative forces. Or in this case, I guess we're calling it QR. Alright, so L is T minus V. So T we had up here was a half mr dot squared. I'm going to memorize my V, which is mgr sine theta. So T minus V is a half mr dot squared, and then V was mgr sine theta. So now, to plug it into our equation, we need di L by di R dot. If I do di by di R dot of what I have there, only the first term has an R dot, and so I get M R dot. Alright, and then what I really need is d by dt of that. So d by dt of M R dot, since M is a constant, this is M R double dot. Then we need the di-L by di-R. If I look at L, the only term that depends on R is the last term, and so if I take a derivative with respect to R, I get minus mg sine theta, right? D by dr just removes the R. And then the QR we've already calculated, that's equal to F. So if I put this all together into my equations of motion, so the red term is mr double dot, then it's minus the blue term, so it's plus mg sine theta, and that's got to equal QR, which is F. If you want, I can write it as mr double dot equals F minus mg sine theta. So that is the equation of motion, right? That's the differential equation that tells me how R depends on time. Right. So that was the goal. And so, it's, as expected, I would say, it's what you would expect from the second law, right? We've done the F equals ma basically in the radial direction, and you have a positive force F in the plus radial direction, and you have a minus mg sine theta, the radial component of gravity in the minus r direction. And so this gives Newton's second law. But we didn't have to, well, we had to write down a vector because of the friction, the non-conservative force. So if the non-conservative force, if there weren't any non-conservative forces, you could see how this problem was just handled with scalars. All we have to do is write down L equals T minus V, and we know how to write T and V in terms of our generalized coordinate, and then we just take those derivatives and we get the equation of motion. So it's a very, very powerful method. Okay, so I was going to do one last little section today. That's the introduction of the generalized potential. Was there any questions about this example? Okay, so let's finish up today with the generalized potential. So previously, we considered the case where the force was given by simply the gradient of a potential. So previously, so just now, we considered the case where effectively the generalized force Qj ended up given by minus di V by di Qj. And we assumed that di V by di Qj dot equals to 0. So we assume that the potential energy, does not depend on velocity. And when we did that, this allowed us to, let's say, put V into the first term of the D'Alembert's equation. So basically it allows us to say that d by dt of di L by di Qj dot, which was d by dt of di by di Qj dot of t minus v equals to d by dt of di capital T by di Qj dot. Right. So we said the di v by di Qj dot is 0. So I can put it into this term that had the d by dt of di T by di Qj, and then that meant I could write D'Alembert's equation with only L's in it. So I can just put L equals T minus V everywhere. Because since V didn't depend on Qj dot, then it didn't matter if I added it into the first term. Okay. So we can generalize this better, and we don't have to necessarily make this restriction. So we can generalize this to the case of what we call monogenic forces. So monogenic forces are the forces where the generalized force this is when we can write the conservative parts of the generalized force. Instead of conservative, we say monogenic. It's a bit misleading for me to label that with a C. So we say that it's monogenic when the generalized force is given by d by dt of di u by di Qj dot minus di u by di Qj, where u is equal to what we call the generalized potential. Of course, what I've really done is I've just rewritten the property of whatever this we call monogenic force. I've just rewritten in the form where now I can very generally put that into the first term of D'Alembert's equation. Alright, so such a force that's given by this is called a monogenic force. So all the conservative forces are monogenic forces. So gravity would fall in this category as well. It's just in the gravity case, the di u by di Qj dot is 0. So for all conservative forces, that first term is 0. But you can always say the conservative forces are a subset of the monogenic forces. So why even bother? Apart, so there's a little bit of mathematically pleasing that we made a more general definition of the potential that's going to allow us to put it into D'Alembert's equation. But does it really make sense for potentials to depend on velocities? So that's like saying the potential energy, should it depend on velocity? Or are there forces that are different depending on velocity? It turns out, yes, there is a force that's different depending on velocity that you already encountered. Not in this course, but hopefully in your career. And so if you think of a force that does actually depend on velocity, the only one you can presumably think of is the magnetic force. The magnetic force is V cross B, right? It's the velocity across this magnetic field. So all because of this magnetic force, it turns out that you do have to consider the case of a potential that depends on velocity. And it turns out you can write E and M in a form that there is a function U, which we'll see in the next example, Thursday presumably. There is a function U that you can write a potential that describes both the electric and the magnetic forces and takes into account the velocity. Okay. So let me write out, so if we use this generalized potential U, then we can define L to be T minus U, and D'Alembert's equation will automatically be satisfied. So we'll say that d by dt of di L by di Qj dot minus di L by di Qj will be equal to the non-monogenic. So whereas previously we potentially had conservative forces, monogenic forces, and really non-conservative forces, the monogenic forces we can include as into L with the conservative forces. Okay? And so in general, we won't distinguish between whether it's a generalized potential or a potential. We just care that we can put it into the Lagrangian as T minus that thing. And so we'll, in general, we'll just call it V. Okay, any questions? Okay, so on Thursday we'll do some examples, and then the next example on the generalized potential I might leave for next Tuesday. We'll see how Thursday goes. Okay, thanks everyone. I'll talk to you all on Thursday.